All right, well, hi folks, my name is Steven. This is going to be a hopefully timely brief on restoring game footage using machine learning. You may notice I am very careful with my words there. This is the what related to those two nasty letters that are very controversial these days, but I chose machine learning because it is more accurate and less triggering. Just to get an idea out here in the audience, how many of you have some sort of computer science background in programming or software development or maintenance or stuff like that? Okay, so a few of you do, most of you do not. That's totally okay. Just to let folks know, I did a similar presentation to this last month at Milwaukee. There are links to those slides in here. That one was more focused on television type stuff. This one is more focused on game footage. All right, well, let's start off with a quick demonstration. So we're going through a little bit of city connection right here. On the left, you'll see the original footage. That is VHS composite footage that I captured of this game. On the right-hand side is the upscaled footage. But what you can see here on a better resolution is that the right-hand side looks a lot better, although it does still retain some of the quirks, I guess you could say, of the original footage. But first, a little bit about me. My name is Steven Reich. I grew up in Janesville, Wisconsin. I have a master's degree in software engineering from the University of Wisconsin-La Crosse. I run a podcast and YouTube channel in my spare time. And I got into machine learning. Again, I'm very careful with my words here. After hearing about some fan remasterings using this technology. There is commercial software that does this type of thing. Not much of it, if any, is related to retro video gaming. But I did want to mention that. I do want to caveat, I am not a professional restoration expert. I do not restore film for a living. I do computer programming, so I don't claim to be an expert in that area. Also, I'm not an optometrist or ophthalmologist. I'm very sorry, kind of, if this presentation feels like going for an eye exam. All right, so what's sort of the gist here? Basically, there's a lot of retro footage out there. In this case, we're talking about video game stuff. You can think about, a lot of you maybe actually recorded yourself playing video games back when you were younger in one way or another. And there's also a lot of commercially available footage out there. And it's, because it was created sometimes decades ago, it just does not have the full fidelity of a modern trailer or anything like that. It'd be nice to clean up some of that. So in the film world, they have to enlarge the picture. There's also video and audio remastering, colorization, and 3D conversion. Not things we worry about too much with video games, but you have some existing methods potentially. With like a TV show, you can see if you can find the original master tapes. If it was shot on film, you can use that. But sometimes you just don't have that. One particular case I designed this video game stuff for was that there's often cases where we will find a videotape of a game that was used at a trade show or something like that. And the game might never have come out. It might have been substantially altered when it actually came out, sometime later. And being able to clean that footage up is a big help in determining, was that really a difference, or is that just a distortion in the tape or something like that? So, just to give you a brief overview of machine learning, 20,000-foot view here, what happens is it's a lot like being on a driving range at a golf course. Imagine that what happens is that it points a laser at the field. Your goal is to hit the ball towards that dot, get as close as you can, and you just practice, and it changes stuff all the time. It has different terrains it can switch between, the wind direction changes. But that's a similar principle here. It's basically using the operations it has at its disposal to figure out the nature between the not so great footage and what it should actually look like, and figure out what are called convolutions. If you've ever used Photoshop, anyone here use Photoshop or a similar photo editing software? Okay. They have these numbered grids that you can use there. And that's how a lot of these things work, is they go over the data, over the image, and make slight adjustments in multiple passes and stuff like that. All right, does anyone else need to have me leave this up for a sec so they can get the slides? I strongly recommend that. I do have a link to that YouTube playlist where I have some of these demo videos that did not really cooperate with the internet connection here. All right. So let me know if any of you have heard of these names here. So there are a variety of frameworks for this type of operation. Sometimes these will be referred to as models. They're not really models, they're really architectures. So I assume some folks here, especially if they're interested in anime upscaling, have heard of Waifu 2X. That is the name of it. Have any of you, so of hands, heard of ESR GAN? Does that ring a bell for anyone out there? All right, that's okay. Next we have OmniSR, and PLKSR is sort of one of the newer ones that came out. These are always being redeveloped, but basically what these frameworks say, they're not a model in and of themselves. They're a structure that says, this is the number of layers it can have, this is what each layer can do. These are some of the mathematical functions you have, some of the operations you can perform on the data when you're transforming it. Now, the other one I'm curious about, has anyone ever here tried to use commercial software? It doesn't have to be game footage, but to upscale a video. Has anyone out there tried this one yet? The one that a lot of folks have heard of is Topaz. Ring any bells for anyone? Okay. And there are a number of others. However, these aren't really well designed for video game footage. They're more designed for live action footage or animation sometimes. So that's one reason I got into this. All right, so to give you another idea of how this works, first you have to build a training data set. And the way it works is that in this case, because we know what it does look like and what it should look like is sort of our goal there. We have a parallel sets of data. We have a low Q, LQ, or LR you might hear, and a high resolution, which is high quality HR, or GT, which stands for ground truth. And in some cases you will use, if you're doing an actual like upscaling model to make the resolution higher, you will use a multiple 2, 3, sometimes even 4. But you can also do ones like this, which is more of a restoration model, which is a 1x thing. Like giving our driving range example, what happens here is that the model is trained in passes, and it basically goes thousands and thousands and thousands of times to get its stuff together. So here's an example of what some training data might look like. At the bottom there you can see Taz from the Genesis Tasmanian Devil game, taking a chunk of the Sega logo there. On the left you have the composite signal. That is the one yellow cable that you get out of this. And then on the right you have RGB, the high quality signal that you can get out of it. Every system is a little bit different. We'll talk about a few examples this way. All right, so here's a bigger view that might give you a better idea of what this is. So as far as our training data goes, here's a nice picture of Mike Tyson. On the left you can see the composite. That has gone to a VHS, been recaptured back. And then the right side is the RGB. That is what we call the ground truth again. So basically what's happening when it's training is trying to use those convolution layers, is another term you might hear, every single time it goes through an image, and trying to get as close to the good image as it can across the whole data set. And we do some things to sort of mess with it a little bit to make sure it doesn't learn the data set too well. All right, so basically, if you ever want to create one of these, the way that works is, first of all, you have to identify your highest quality source. So for the NES/Famicom model I created, I used a device called the RGB Blaster. It's made by a guy by the name of Crix. Some of you might know about some of his other products. But this was very useful in that it doesn't require your system to be modded. It actually goes in between the cartridge of the game and the system. It's an interesting little device that way. For the Sega Genesis, for my ground truth data, I had what's called a triple bypass Model 3. Oh, I'm sorry, that should be a Model 2. I have that mistyped there. And that basically, they replaced the capacitors, they fixed the audio issues on the Model 2 that are pretty prevalent, and they also redid all the video circuitry and actually did everything they pretty much could on real hardware. And once you got your ground truth source picked out, you got to do your other types. I've used, like I said, composite, RF, even VHS. I still have a working VHS player that I put stuff on and get it back. All right, we'll do a couple case studies now. This is the NES/Famicom. I assume everyone's familiar with the NES pretty much. The Famicom is just the Japanese version. There are some technical versions, like you may notice if you look here today at some of the import games, the Famicom games cartridges are smaller than the NES ones. Whole other story. These systems mostly only support RF and composite out of the box. And one of the distinct things they have is they have this crunchy video output. Here's a close-up of the title screen of the NES version of Tetris. And you can notice on the edges, especially around the colored, the parts with color, is that you have these weird ridges on there. It's very crunchy, and that's a very typical artifact of the NES picture processing unit in all its variations. So what did I do for a data set here? So I use that RGB blaster, and in order for the data set to work, you need to have pictures that are the same between, frames that are the same between the good ground truth quality stuff and the low resolution stuff. Now, on a TV show, you might look for see if a related TV show has like a DVD and a Blu-ray version. For this, though, what I was able to do, a lot of older video games and even some newer ones have what's called an attract sequence or a demo sequence. This was dated back from the arcade where the game would play itself for 5, 10, sometimes longer seconds, and it would show you parts of the game to get you to come in and play it. So you've probably seen that, and that was how I got my exact same frames. For the most part. I didn't have to worry then about putting in the exact same inputs and stuff like that in order to get it. Then I just had to capture that video, like you do, and then I aligned everything to the nearest pixel. Since this is a 1x scale, it's a lot easier than when you have to do like a 2x and really align stuff. Yeah, so you train the framework, it's a 1x scale. Depending on the size of your network, that'll determine how many operations it gets to use. People are always trying to do different things in terms of like, you have to do, the bigger the model, usually the longer it takes to process stuff, but the more things it can do. And the newer models try to always have to balance quality versus speed and stuff. PLKSR is sort of the newest one. It does a pretty good job on fixing some of those artifacts. All right, so you saw that video maybe at the beginning, if we didn't have all those connection issues. The teething was removed, but there are some quirks of the NES I haven't been able to fix. Basically, a lot of retro video game systems in their regular resolution mode is called like 240p, and it renders like half a frame of video effectively, so it does 60 frames per second, but they're half height images effectively in a way. And sort of the problem with the NES is that it's even in odd fields, which is what those separated frames are called, don't quite work exactly the same, and you get some weird jitter there depending on your capture setup and whatnot. It's especially noticeable with the colors. If you take a look at some of the color stuff, that stuff jostles around a bit more. All right, well, let's talk about the Sega Genesis, the other model I've made so far. This was released in the late 1980s. It does actually have native RGB support. The Nintendo base hardware does not for that system. Although the quality varies by revision model when they would swap out chips and they make little tweaks there. So at the bottom there, you can see a little bit of a title card from Sonic the Hedgehog 2 for Casino Night Zone. And this is RGB video from a Model 1. The problem is it has these what are called jail bars, which are these very faint vertical lines, hopefully you can see in there. So this one I used the Model 2 footage. I used a couple different Model 1s for the footage as well as the VCR and stuff. So that was kind of fun to work on as part of this. All right, well, let's see if this one decides to work. And if so, this is going to see a little footage. This is Sonic 2. This is a couple of attract sequences from that. Left-hand side is going to be RF. Right-hand side is going to be the upscale. So let's see if this one cooperates a little bit more. So far, so good. You can see the colors are a little bit different. The contrast is much better on the right-hand side. But we're going to go through about 2 of these. Or maybe just one on there. We'll see. I do have a nice little clock here. I know I don't have a ton of time left. How it's a lot sharper on the right-hand side and stuff. It can't get rid of all those color artifacts. The Genesis is very well known for having some odd artifacts that were sometimes used intentionally by developers. So, possible improvements. More console revisions always helps me. Tweaks to the training programs. And oh, by the way, like a lot of stuff in machine learning, this requires a GPU, not necessarily to run yourself. You can always run it on a CPU, but to actually train it in any reasonable amount of time, you're going to want a GPU. And if anyone knows someone who works in video restoration or production, and that, I would always appreciate that. All right, so what you're probably wondering is, how do I actually use this? Well, You can talk to me afterwards if you want to learn how to actually create a model, but as far as using these models, first of all, I recommend an NVIDIA GPU for this. It doesn't have to be super fast unless you plan on doing large amounts of data. It is relatively slow to go through this. You will get a couple frames per second converted at a time, fair warning. But there's a place called the Open Model Database that has lots of models like mine, some for specific TV shows, some for specific mediums, so on and so forth. What you're going to have to do is process the source footage, which is a topic in and of itself, because you have to, going back to that 240p thing I mentioned earlier, there's a specific way you have to process the footage to get the best results. And then there's this little application for Mac, PC, or Mac, Windows, and Linux called Chainer, which is a node-based piece of software, and it supports most of the major frameworks in there, so if you want to process some videos. I know this probably looks a little intimidating, but if you get the slides, remember I have the QR code up one more time at the end of this. This is a very basic one where it loads a video on the left, loads a model on the left, upscales the image. It treats every frame as a separate image effectively, so it goes frame by frame by frame. The text append is just to make sure it's a different file name, and then it saves the video out, copies the audio over, keeps the same in. But you can download that template off of my MediaFire account, and if you want to play with this a little bit, and like I said, go to the Open Model database. All right, questions? Does anyone have a quick question they want to ask about this? I have, like I said, on my computer, all this stuff here. Yeah, take that photo. Like I said, it's a MediaFire link. You'll get to the slides for this presentation. It's one of those things that's it's easier than you think, but harder than you'd like, is sort of the way I put it there. All right, well, thank you very much, folks. I can answer some questions and show some demo reels afterwards. If folks want to see that, I'll be right around here for at least a little while. But thank you very much for your time. I appreciate that.